About to go the distance in Measure for Measure, Lengths and Heights.
First, we'll learn about the measuring devices sailors use to navigate the seven seas in perfect measurements.
Next, we'll see how undersea disturbances can create killer waves 10 stories tall and send them crashing into coasts thousands of miles away in Waves of Destruction.
Next, we'll go back in time and meet the people who carved up our world into inches, yards, meters, and miles in Going the Distance.
Then we'll trace the lengthy trip that billions of blood cells take with every heartbeat in the Heart of Hell.
Finally, we'll watch what happens to a climber's body as he attempts to scale the highest peak on the planet, Mount Everest, in the height of illness.
Longer lengths and higher heights coming up next.
As you watch the first half of this program, keep these questions in mind.
What timekeeping devices do sailors use to navigate?
Why are standardized measurements important?
Navigating the world's oceans is not an easy task. Centuries ago, seafarers learned how to calculate their longitude and latitude by measuring the position of the sun or stars. But more recent devices have helped them find their way in the ocean with almost perfect precision.
If you were lost, how would you find your way?
I think the first thing to do would be think about the position maybe of the sun.
I would watch the sun rise in the east and know it sets in the west and find my direction from that.
I'd probably look in my rucksack to see if I had a compass.
A compass would be a logical way to get out, but I would use a cell phone.
My cell phone has this GPS component to it.
If I saw some light, I would walk towards that, or if I saw someone there, I'd ask for directions.
The aircraft carrier George Washington is one of the most sophisticated ships afloat. To find their way in the ocean, these sailors have every conceivable high-tech navigation instrument. So what in the world are these sailors doing still using the stars to navigate? And why is their key piece of equipment an accurate clock? This centuries-old technology still has relevance today. And here's why. You can use just the stars to determine your latitude, which is your position north or south. But to determine your longitude, your position east or west from the prime meridian, you also need to know the difference in time between your location and a fixed location. And for that, you need an accurate clock. Having the wrong time could result in being off course by hundreds of kilometers east or west. This was the situation that sailors faced centuries ago. When scientists speak of the accuracy of a measurement, they mean how close the measurement comes to the real value. Using star charts allowed sailors to measure the local time accurately. Until a couple of hundred years ago, there was no way to keep a clock accurate on board a ship. And using the sun and stars to tell time was not accurate enough to determine exact longitude. Astronomers at the Royal Observatory in Greenwich, England, offered a solution to one part of the problem. They published an almanac showing the positions of the stars over Greenwich at any time of the day on any day of the year. Sailors used a tool called a sextant to measure the distance of a star from the horizon. By comparing their findings to the charts in the almanac, sailors could determine the local time much more accurately. Greenwich also became the fixed location for time measurement, but sailors still needed a way to keep track of that time.
We have predetermined stars that we've gone and figured out for to shoot, which is ahead of the bodies. For example, we shoot Kodiak, and we take the star down to the horizon. The most important thing about using celestial bodies, be it the sun, the stars, the moon, or the planets, is time. Everything is related to time.
By using new technologies, the sailors on the George Washington can measure the local time and compare it to the time in Greenwich. But centuries ago, the only existing clocks were pendulum clocks. They couldn't be used on moving ships because the ship's movement on the ocean disrupted the pendulum's regular movement. A race began for a mechanical clock, or chronometer, a device that could keep accurate time on the open sea. Jim Michaels, a modern-day watchmaker, explains the history of this device.
There was a commission set up in England that would offer a prize of 20,000 pounds, I believe it was, to anyone who could come up with a chronometer that would meet very strict standards.
The year was 1714, and the man who stepped up to the challenge was a carpenter named John Harrison. He spent 40 years developing a marine chronometer, a hairspring mechanism that replaced pendulums. During a final test voyage to the Caribbean, it lost only 7 seconds. Harrison won the 20,000 pounds, which translates to $12 million today. It was a worthwhile expenditure, according to the navigator of the $3 billion George Washington. The invention of the chronometer was a major step in the technological advancements that helped the navigator of the George Washington do his job.
What we're doing right now is setting ourselves into the wind, which we are. We're coming up on speed so we can get the minimum winds over the deck for the heaviest aircraft, which in this case is going to be an A6 tanker.
The carrier must always be moving, either into the wind for takeoffs or downwind for landings. With all this turning and maneuvering, it would be easy to get off course. The first line of action is to use satellites and the Global Positioning System, or GPS. Sextants provide a reliable backup.
If something does go wrong with the electronics, if a satellite fails for one reason or another, I have my quartermasters that can still shoot the stars and still give me a good fix. And as you can see, where we plotted our fix today was within 1,000 yards or less of where the GPS had us, which is extremely accurate in open ocean.
Satellites can fail, but the stars remain a constant. That is why every day on this high-tech vessel, the quartermasters still shoot the stars. They still check the ship's clocks, and they report their status to the captain.
Sir Deck sends his respects and reports the approaching hour of 12 o'clock. All chronometers have been compared. Customers should strike 8 bells on time.
Strike 8 bells on time.
Did you know? The moving parts in John Harrison's marine chronometer were controlled and counterbalanced by springs. This meant that unlike a pendulum clock, it was independent of the direction of gravity. The linked balance mechanism ensured that any change in motion that affected one of the balances was compensated for by the same effect on the other balance.
Tsunamis form hundreds of kilometers out at sea when underwater disturbances create harmless waves on the ocean's surface. But by the time these waves reach the coast, they can surge into towering walls of water that are truly terrifying things to behold.
What's one of the longest or tallest things you've ever seen?
The tallest thing I've ever seen is probably a mountain.
The Eiffel Tower is pretty huge.
The CN Tower in Toronto.
Probably the Sears Tower.
The World Trade Center. That was the tallest thing I've ever seen because I was standing like right under it. As soon as you come out, you just look up. Sometimes I've actually fallen backwards trying to look up at the whole thing.
The longest thing I've ever seen is probably a long beach.
The Great Wall of China.
Well, highways seem really long when you're driving on them.
The Brooklyn Bridge is very long.
I've seen really long snakes on TV, pythons.
walkovers.
I've seen, well, a picture in the Guinness Book of World Records. It was like the longest piece of pasta. It was like, it's really long.
Ocean waves look like they're transporting water with them wherever they go. But waves aren't really moving water. They're moving energy. A water molecule in a wave, shown here by a red dot, actually moves up and down in a circular orbit, not sideways. It's the energy in the wave that moves through the water. Tsunamis, like all waves, are made of a series of crests and troughs. But unlike typical ocean waves, which usually have wavelengths between 40 and 400 meters long, tsunamis typically have wavelengths between 100 and 700 kilometers long. Normal ocean waves are produced when wind transfers some of its energy as it pushes along the water's surface. But tsunamis are caused by a number of different high-energy events. Tsunamis are most often caused by underwater earthquakes that violently shake and move the seafloor. The entire depth of water above the point of the earthquake is driven up and down by the energy that moves the ocean floor. Landslides above and below ground can cause tsunamis. If the slide happens underwater, the falling rocks displace the water around them and create a tsunami that travels outward from the origin of the slide. When Mount St. Helens erupted in Washington State in 1980, it created a massive landslide that crashed into a lake, creating a wave 250 meters high. Underwater volcanoes can also trigger tsunamis. When they erupt, they also cause large quantities of water to move. Although these are less common, they can be just as deadly. Tsunamis can travel at speeds up to 720 kilometers an hour. That's more than half the speed of sound. Tsunamis out here may only be a meter high. Someone on a ship might not even feel one of the waves as it passes beneath them. But when tsunamis approach the shore, the rising sea floor forces the wave to rise. It builds, then breaks into a huge surge of water. The Japanese are taking a different approach to protecting themselves from tsunamis. Here, many coastal towns are rapidly disappearing behind larger and larger barriers of concrete. After 2 major tsunamis, the people of Taro started building protective walls. They now have 3 of them, but even these massive structures will not be enough to shield Taro from the biggest tsunamis. One of the best ways to avoid loss of life from tsunamis is to get out of their way, so detection is key. Helping in this challenge is a deep-sea pressure monitoring system developed by this team at the Pacific Marine Environmental Lab in Seattle. At the heart of this system is a pressure gauge, which is lowered to the ocean depths.
The most amazing thing about this device is that it's capable, when placed 3 miles deep in the ocean, of measuring a tsunami about 1 millimeter in height.
The gauge transmits its measurements to a buoy on the surface, which relays the information via satellite.
You can see it's kind of drifting around. We're getting back closer here, dude. Did you get a mark on the screen where it is? No, if someone can give me that position.
A computer monitors the data, searching for the unique pattern of a tsunami. The team is working on setting up a line of gauges across the North Pacific. When they're in place, the gauges will detect any incoming tsunamis, so accurate warnings can be distributed to likely impact sites. As an added bonus, the data collected by pressure and tide sensors can help surfers and water sport enthusiasts know where they can catch the next best non-tsunami wave. In the places where they exist, warning systems are helping to reduce the risk to human life. Although we may never be able to stop tsunamis from hitting populated areas, modern scientific advances like these are helping to make our coastlines safer every day.
Did you know The word tsunami comes from Japan, where it means harbor wave. One of the worst tsunamis to strike Japan hit the town of Sanriku in 1896. The wave was less than half a meter high when it began at sea. But by the time the wave reached port, it was 38 meters high, and it killed 28,000 people.
Thanks to the metric system, the word meter means the same thing in whatever country you're in. But in the past, different countries had their own measurements and words to describe units of length.
What's the longest word you know?
The longest word I know of is anti-disestablishmentarianism.
Supercalifragilisticexpialidocious. There's one longer than anti-disestablishmentarianism, but I can't remember what it is.
Should I try to spell it? ANTIDISESTABLI. Hold on, let me start over.
Immunopathology. Departmentalization. Onomatopoeia is the longest word I know.
Anti-disestablishmentarianism.
ANTIDISESTABL. I need to write it down. That's as far as I can get.
Measurement rules our lives. It has sliced up our world and helped us impose order and logic on our restless universe. Where would we be without kilograms and grams, minutes and seconds, meters and miles?
Remember, there is a 5-mile tailback already from junction 2.
These are your allies. The fight to take in fewer calories.
Like a big failure beating yourself over the head because you broke your diet.
Night to follow with poor curbside air quality. Today's high, a scorching 30 degrees Celsius. That's 86 Fahrenheit. In town tonight, no lower than 20. That's 68 Fahrenheit.
At the third stroke, the time sponsored by Accurist will be 4:44 precisely.
Nowadays, we take measurement for granted. But how did it all start? In the beginning, man was his own measure. 2 steps made 1 pace. 1,000 paces made a mile. Fingertip to fingertip made a fathom. That's 6 feet. And the distance around a man was a girth, or 3 feet. But what was a foot? Well, the foot was a foot, like the hand was a hand. The finger was a finger, and the span was a span from pinky to thumb. But the ruler was the elbow. Or, as it was better known by its Latin name, the cubit, the distance between elbow and fingertip. According to the Old Testament, Goliath measured 6 cubits and a span, and the ancient Egyptians used cubit rulers to achieve their uncanny precision. The sides of the pyramids of Giza are 230 meters long. That's about 750 feet, and they're only off by this much. A stadium in ancient Greece was said to be the distance that the mythological hero Hercules could cover while holding his breath. He managed the equivalent of about 200 modern meters, and this fixed the length of the running track at Olympia, home of the first Olympic Games. But as a unit of length, the stadium's days were numbered. The foot fared better. It has ambled around different civilizations for thousands of years. it's been 10 modern inches, 13 inches, 17, and even a Herculean 27 inches. In ancient Rome, the foot was the length of a copper bar that had been made to weigh exactly 1 pound. The bar was divided into 12 equal parts called unciae. As a unit of both weight and length, it was the source of the modern terms ounce and inch. In 16th century Germany, a foot was determined by asking 16 men to line up after church to have their left feet measured. The sum was divided by 16. Doing the same today with 16 males gives a length that falls a little short of expectations.
Sounds like baby pattern. Baby elephant pattern, that's what I call it. Stand up in Harlem at a table for two. There were 4 of us, me, your Big Pete, and you.
Originally, shoes came in only 2 sizes, small for women and large for men. Now there's a size to fit anyone. Shoe sizes have always been linked with corns. Corns of barley, that is. By laying barley corns end to end, you can determine shoe sizes. One barley corn is 1/3 of an inch. In 1305, Edward I laid 3 corns end to end. He proclaimed that this length would become the inch.
My girl can be tied. She can really be.
Unfortunately, feet, corns, and other natural products were unreliable as a constant standard of measurement. Different units of length plagued the first traders. They never knew how much of anything they were buying. They needed an absolute standard. Henry I decreed that the standard yard was to be the distance from his nose to his fingertips. He commanded that an iron bar be forged to this length. It became the royal right to set the standard. And over the years, several monarchies remodeled the yard to match their own measurements. Henry VII made it the length of his arm. Her Majesty Queen Elizabeth I wanted to put her own stamp on Henry's yard. Adding her E took it up to almost 36 inches. The noble standard traveled down through generations, giving the kingdom continuity and stability, but the world was on the move. The 18th century brought a surge of scientific experimentation and new knowledge. For the first time, the crudely fashioned, somewhat elderly yard was found wanting. And then, fate intervened. In 1834, a mighty fire ravaged the houses of the British Parliament. One of the most precious pieces of metal in the land, the Standard Yard, was burned to a crisp. The scientists saw their chance. Now, they could dispense with an arbitrary system based on the length of some monarch's limb. They wanted the new yard to be based on laws of science so it could always be accurately reproduced. So, where did they look? To a pendulum. In 1581, 17-year-old Galileo was fascinated by a candelabra he saw swinging in Pisa Cathedral. He timed to the candelabra's swings with his pulse and observed that the time it took to travel from one end of its swing to the other was always the same. As he later proved, it made no difference whether the swing was big or small. The length of the pendulum precisely determined how long the swing lasted. This was the principle the scientists wanted to exploit. Their yard was to be the length of a pendulum that would generate a swing that would last exactly 1 second. On paper, the theory was sound, but in practice, they couldn't make it work. The fluctuating effects of gravity upset their designs. To their dismay, they had to settle for something simpler. They still had copies of the old standard that had been destroyed in the fire. They decided that the new yard should be the average length of these copies. They set about building the most sophisticated and precise measuring apparatus ever made. Super-sensitive thermometers were specially made because the scientists knew that even the tiniest variations in temperature could affect the length of the metal bars. Soon they were ready to begin. Every bar was compared to every other bar many times and in every possible position. Several men repeated identical experiments to minimize the risk of human error. It was a huge task. They recorded more than 200,000 readings, and it took more than 12 years to finish. Finally, they had their average. Next, they formulated a very stable metal. They cast 40 bars from it, and the best was designated number 1, standard yard. Tragically, the scientist driving this effort, Reverend Richard Sheepshanks, died 1 day before his yard was to receive royal approval. One copy of his brand new yard was granted an official home in the rebuilt Parliament. This time, every precaution was taken to keep it safe. Sealed in a fireproof box, it was bricked up in a wall, where it resides to this day. Other copies were dispatched to the colonies. And one was presented to America, where it became the national standard too. But alarmingly, measurements soon revealed that the new yard was not stable after all. The bronze bars were shrinking. American colonists began using the French meter as a more reliable reference for the yard. The British yard kept on shrinking, but not by much. If you measured the distance across the United States first with the British yard, then with the American one, the difference between the two would only be 10 yards. Sounds trivial perhaps, but it was enough to cause problems in World War II, when aircraft components made in one country were not compatible with those made in another. Already the fate of the yard was in doubt. Some predicted that the end of the 36-inch ruler would soon arrive. the unstoppable march of metric conversion will have assigned the yard to history. Out of the chaos and confusion of the French Revolution emerged the precise logic of the metric system. It was part of the new thinking, a reaction against the iron grip of tradition. Up until then, measurement in France had been a mess, with thousands of different standards in common use. The new metric system was the first to be planned from principles. Its starting point was to be the new unit of length. Scientists proposed that this new unit, the meter, not come from the human body or seeds of a plant, but from an established scientific constant. 1 meter would measure the circumference of the Earth, 1/10,000,000th of the distance between the North Pole and the equator. Realizing that it was impractical to measure the entire distance, they opted for a sector between Dunkirk and Barcelona. The survey began in 1792, amid the turmoil of revolution. The scientists didn't laboriously measure the whole distance by hand. Instead, they used a technique called triangulation. One line, the baseline, was measured as accurately as possible. From either end of this line, they measured the angles to the third distant point, such as a mountain peak. With this information, they could use trigonometry to calculate the distance to the mountain peak. By plotting a network of triangles between Dunkirk and Barcelona, the total distance could be calculated to a very high degree of accuracy. The men given the job had no idea what they were letting themselves in for. Wherever they went, they encountered suspicion and hostility. It was hardly surprising. They were a group of strangers from Paris, carrying strange machinery and claiming to be measuring the world. What's more, their surveying flags were white. And in France, white was the royal color, so it appeared they were agents of the king. The unfortunate scientists were constantly detained, questioned, threatened, and arrested. The survey was to take 10 difficult years. By the end, several of them had been imprisoned. Some faced an even worse fate. Mathematicians used the survey results to calculate the distance from the pole to the equator. Then they constructed a platinum and iridium bar precisely 1/10,000,000th of this distance. Stand aside, cubit, yard, and chain. Be gone, barleycorn, inch, and foot. Make way for the meter. Alas, later scientists discovered that the Earth was not a regular shape. Yet again, the length of the meter was inconsistent with the fundamental length. So it was back to the drawing board. Now at last we've got it right, but it's taken centuries to get here. It comes down to the speed of light. It's speedy, but at least it's constant. The meter is now the distance traveled by a beam of light in a tiny fraction of a second. To be precise, almost. You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
What timekeeping devices do sailors use to navigate?
Why are standardized measurements important?
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
As you watch the second half of this program, keep these questions in mind.
How does the circulatory system move fuel and waste products through the body?
How does high altitude make breathing difficult?
You may have been on some long trips in your life, but none of them even comes close to the 100,000-kilometer-long collection of blood vessels inside your body that make up the circulatory system.
What's the longest trip you've ever been on?
I've flown from New York to Japan once.
I traveled from New Jersey to England.
We went to Germany.
I flew in a plane to Egypt. Probably took like around 14, 16 hours.
The longest race I ran for cross country was 2.1 miles.
On my bike, I went around my town for 15 miles. That was pretty long.
The longest car rides I ever took was to Florida. I was probably in the car for about 12 hours.
We were in a Suburban with my dog, my friend, and my two brothers, and my mom and dad.
It was so boring and it's so hot in that car, and it's the middle of summer.
And it was horrible.
This is George. He's been neglecting his body for years. He's eaten unhealthy foods and hasn't exercised regularly. Part of the problem is that he enjoys eating foods high in cholesterol. Cholesterol is a waxy fat-like substance found in animal products. After George eats, the cholesterol in the food eventually enters his cardiovascular or circulatory system. The circulatory system is a complex network that transports blood through the body. It is made up of the heart, blood, and a system of channels called blood vessels. Blood flows through these blood vessels, delivering oxygen and the nutrients our cells need to function. But our friend George, like many other people, has been eating a diet with too much fat in it. Fat is one of the main causes of problems in the cardiovascular system. As excess fat and cholesterol flow through George's system, they cling to the walls of his blood vessels and form a sticky lining. Over time, these sticky buildups have limited the amount of blood and oxygen that can flow through his blood vessels, and they have reduced the nutrients his cells get to absorb. So after getting his doctor's approval, George has decided to get into better shape. But it might be harder than he thinks. Years of neglect have made his circulatory system less efficient than it could be. After warming up, George hits the treadmill. This is one of George's leg muscles. His bad diet and lack of exercise has made the blood vessels leading to and from his muscles narrow and weak. As he exercises, his muscles require increased amounts of oxygen and fuel, and waste products made by his working muscles begin to build up. George's inefficient circulatory system isn't able to meet his body's demands. He is overwhelmed. He thinks his trip to the gym was a flop, but something is beginning to change inside George's body. With repeated exercise, new blood vessels will develop in George's muscles, increasing the supply of blood and fuel he can use. As George continues exercising and eating sensibly, he begins to notice the difference. More oxygen and nutrients are circulating through his system and making their way to his cells. His stores of fat are shrinking, and his muscles are becoming more efficient. Thanks to exercise and a healthful diet, George has gotten into better shape, and so has his circulatory system. Most of us can improve our cardiovascular systems by eating a better diet and exercising more. But top athletes regularly push their bodies to the limit. Their intense exercise regimens have an equally intense effect on their circulatory systems. Bobby Thatcher is a good example. He's an Olympic hopeful in rowing, and this early morning workout is just one part of his intense training program. To make the team, Bobby must work continually to improve his performance. Rowers cannot function at their peak unless their cardiovascular systems are at their peak as well. Understanding how his cardiovascular system works helps Bobby gain the edge he needs. Rowing may look peaceful on the surface, but inside Bobby's chest, his heart is pounding, delivering blood through his blood vessels to his leg, arm, and chest muscles. Blood carries oxygen from our lungs to the rest of our cells. It also carries fuels like glucose and fat that our cells need to produce energy. So the body can operate at peak efficiency, it needs a good supply of oxygen. As we exercise, our breathing speeds up to get more oxygen into our system. And the heart beats faster to pump more oxygen-rich blood through our blood vessels and to our straining muscles. The circulatory system is made up of two interweaving loops. The heart is at the center of the system. In the first loop, called pulmonary circulation, blood is pumped out of one side of the heart and travels to the lungs, where it picks up oxygen and then travels back to the heart. In the second loop, called systemic circulation, the oxygenated blood is pumped to the rest of the body. As blood is pumped through the body, it delivers oxygen and other nutrients and picks up waste products. The oxygen-depleted blood then makes its way back to the heart, where it starts the cycle all over again.
Okay, get ready for this piece.
It's time to test Bobby's training on the water and in a dry run in the lab.
Come forward. Set. Go.
Go.
Hours in the lab have taught Bobby how to get the most out of his body. He has rehearsed the grueling race under intense scrutiny.
That's it. Nice and sharp off. Well done.
As Bobby begins his test run, his muscles spring into action. They need more blood and the oxygen and fuel it carries to keep them going. His heart rate speeds up. With each beat of his heart, blood is pushed through the blood vessels of his circulatory system. At rest, it takes less than a minute for his heart to circulate blood through the arteries and veins that make up his blood vessels. During exercise, it takes even less time. Bobby's heart has revved to twice its normal rate because his blood must carry more oxygen to feed his straining muscles. As our muscles work, they produce a waste product called carbon dioxide. But our circulatory system has a way of getting rid of this waste. After it enters the bloodstream, carbon dioxide is carried by the blood to the lungs, where it is exhaled into the air. Having blood flowing efficiently throughout the body is essential for removing these waste products quickly. And the heat our muscles produce is another byproduct that the circulatory system helps to eliminate. The blood absorbs this heat and transports it towards the skin's surface so that the outside air can cool it down. When a muscle is working, the skin above it warms up several degrees. Sweat, which is formed from water inside the body, is another means of keeping cool. As sweat evaporates from the skin, it lowers the skin's temperature. In the lab, Bobby is ready for his final sprint. Is his cardiovascular system up to the test? He increases his stroke rate. He fills his lungs to the maximum capacity, and his heart starts pumping more quickly. But Bobby's heart is actually beating slower than yours or mine might. His years of training have given him what is called athlete's heart. His heart's main pumping chamber, the left ventricle, has grown bigger and can pump more blood with each beat. That means Bobby's heart doesn't need to beat as often to get the same amount of blood circulating through his body as a less conditioned heart would.
15 seconds to go. Right now, 36.
His well-conditioned circulatory system improves his ability to get oxygen to his muscles and remove carbon dioxide wastes, which means his muscles can work more efficiently. And more efficient muscles translate into a better time in the race. Bobby is one step closer to his Olympic dream. It has taken dedication, intensive training, a good diet, and a healthy, efficient circulatory system to get him here. Did you know? The path your blood takes through the circulatory system is a long one, but it takes a blood cell only 30 seconds to complete the cycle. A healthy heart pushes about 7 tons of fresh blood through the body every day and beats an average of 2.5 billion times over the course of a lifetime.
Mountain climbers aren't scared of heights, but there are other dangers to high altitudes. Reduced oxygen in the air makes breathing difficult, and climbers have to take special precautions to avoid a life-threatening condition called altitude sickness.
What's the highest place you've ever been?
The highest place that I've ever been was when I went to the Statue of Liberty.
Mount Vesuvius in Pompeii.
On a plateau in Wyoming that was a little above 7,000 feet.
On top of the Twin Towers.
Well, I know it's not that high, but I have stood right there by Niagara Falls, right where the falls goes down on the Canadian side.
When we went to Hawaii over the summer, we climbed a volcano.
I went to Kilauea, Iki, and Mauna Loa, and they were both volcanoes, and so they're really high above the land. You can see them from other islands.
This group of climbers has just arrived on base camp on Mount Everest, 5 kilometers above sea level. Guy Cotter, climber Andy Hebson, and Dr. Dave Hiddleston make up the expert guides of the group.
All right, Andy. Okay. Welcome to base camp, buddy.
As the physician on the climb, Dr. Hiddleston needs to impress on the climbers the need for effective respiration. Breathing is key to the respiration process, supplying oxygen to the blood so the blood can deliver it to all parts of the body.
Right through.
The climbers must take in enough air to provide their cells with the oxygen they need to function properly. It is especially important for the brain and muscle cells to have the oxygen they need. The trek will become more perilous as the climbers continue. Just to give you an idea, at base camp, the air is 42% thinner than it is at sea level. With less oxygen getting to the body's cells, the climbers run the risk of becoming vulnerable to altitude sickness.
Truthfully, I would like to summit. I've trained for 2 years to get ready for it. I've done a bunch of preliminary climbs. I climbed in Latin America and in Shoyu and trying to work up to this point. So. But I would be, as long as I put out, and it's my best effort, whatever, as far as I get is as far as I get. But I really would love to summit this thing.
The extreme altitude of Mount Everest makes it impossible to climb without serious preparation. Before a summit attempt can even be made, a month-long acclimatization program has to be undertaken. Climbing up and down the mountain to camps at roughly 0.7-kilometer intervals. The first day's climb is to Camp 1, 0.58 kilometers above base camp. Only a matter of hours will be spent there, just enough time for the body to adjust.
The body has to acclimatize. That's a process that takes several weeks actually to be fully completed. It starts out just by breathing deeply and gasping for air. That's when people feel short of breath because they're trying to get more oxygen. And after a while you get used to that and you begin to breathe easier because your body brings in other processes such as increasing the number of red blood cells which carry oxygen. It makes it easier for you to transport the oxygen to your tissues. Those processes take weeks.
Back at base camp, at least one of the climbers is already feeling the effects of oxygen deprivation.
Hey, Andy.
Nauseated.
Andy is suffering from headaches and nausea, common symptoms of altitude sickness.
There you go. One white one.
One white one.
One more green one for...
Another doctor at the camp prescribes medication that will help Andy breathe faster so that he can take in and metabolize more oxygen. The next day at base camp, Andy feels well enough to continue his climb. He sets off for Camp 2, 6.4 kilometers above sea level. As he climbs higher, the number of oxygen molecules in the air continues to decrease. To compensate, Andy's breathing rate must increase even more to try to get more oxygen into the blood. The lack of oxygen is affecting the cell's ability to function.
When I was fairly close to Camp 2, I was trying just to get 4 or 5 steps, and I was actually seeing dots. I couldn't even hardly breathe. Felt like I had a garbage bag in my left lung.
Andy has to spend the night breathing bottled oxygen. Its high density of oxygen should help him regain some of his lost strength.
Health is very, very important up high. And if you're unhealthy, your chances of doing well at altitude are reduced severely.
The next day, Andy decides he is not well enough to continue. His Everest dream is over. Although Andy had a difficult decision to make, he made a wise choice.
Rachel, bye now.
Oh, see
you on the next one.
The only sure way to recover from altitude sickness is by descending the mountain to where there's enough oxygen for the body's oxygen-depleted cells.
You know, I'm disappointed that I didn't summit, but I'm not done yet. I'll be back. All I'm going to do right now is back up a little bit and take another run at the hill. So, yeah, that's my plan.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How does the circulatory system move fuel and waste products through the body?
How does high altitude make breathing difficult?
We hope you've enjoyed this assignment discovery journey into the meaning of measurement. If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
That's a wrap for today, but tune in next time as we explore the extremes of time and temperature. We'll fast forward through billions of years to witness the death of a star. Zoom back through time to examine what killed the dinosaurs. Learn how Fahrenheit, Celsius, and Kelvin scales measure temperature differently. And watch as researchers use this information to predict where and when hurricanes will strike. Join us next time for Measure for Measure, Time and Temperature, here on Assignment Discovery.
The preceding program is part of Cable in the Classroom, a free service of the cable telecommunications industry and your local cable company.